can you see my screen?
Yeah, it's fine, thanks.
Okay. Okay, so these slides are sort of an updated version of a talk I gave, I think, 2 weeks ago for some people who are less experts. I'm going to just sort of skip through some of these first slides. I managed to put a meerkat in. Okay, so you all know, you know, that this is sort of the mantra of intensity mapping. So I won't go over this, but in terms of looking at an off-axis telescope, we sort of thought that the hardest thing in terms of antenna requirements was for the intensity mapping, so that we would just look at this as a design criterion, or focus on the hardest thing that you can really do. And let's see. Okay, so we want to sort of look at our ability to recover the baryon acoustic oscillations, and then that sort of translates into cosmology and all of that, and that's well known. So there's sort of two routes. One could be, you know, end-to-end simulation. So you have these designs, and then you make a pipeline, and then you have to make all sorts of other assumptions about the instrument. And unless those are parts of the design that you're sure of it, you know, you get a final number at the end. It's kind of slow, and that would be the sort of might be the optimal optimization, but it's sort of nice to sort of find some sort of imperfect, simple criteria to evaluate antenna designs. So that's sort of what we try to do here. And basically, you have the galaxy, and the galaxy has this, you know, power spectrum that sort of factorizes, and a part that's sort of the angular part, K perp and K parallel. So here we're just going to sort of look around the main beam. We might try to do side lobes a bit later, and side lobes are, you know, really far side lobes that see the ground, and the other antennas are a big problem. I mean, with the other antennas, that depends on whether you're pointing at the zenith or where you're pointing, and the ground is neither perfectly absorbing nor perfectly reflecting. And water is important. So if the ground is wet, it'll behave differently from if the ground is dry, etc. I had a long discussion with someone from Schlumberger about the dielectric constant of the ground. So for people who do oil, searching for oil, they use the dielectric properties of the ground as sort of a diagnostic. So we're just, as Carla pointed out, we flatten the sky, we apodize away the far side lobes and just focus on sort of the near side lobes that are still pointing in the sky. And okay, the extragalactic is the cosmological signal, and then modulo redshift distortion, which we ignore, at least for this figure of merit, that isn't a problem. So if you have a linear measurement process, then we have sort of equation 3, where there's some sort of a linear transfer function with noise put on it. And in terms of the antenna pattern, it really comes into the matrix M. So we're going to just represent some of this stuff sort of abstractly. And unless the matrix M is singular or something like that, I mean, you could take the attitude, oh, well, we don't really care about the antenna pattern as long as we can measure it. Having a weird antenna pattern isn't really a problem. So after a lot of thought, we concluded, well, there's going to be uncertainty in the antenna pattern. So there are problems in fabrication. There are also problems with simulations. The simulations aren't infinitely accurate. The materials aren't like these perfect electric conductors used in the simulations. So to sort of jump ahead a little, what we think is most important with a good antenna pattern is you don't want to mix modes that are sort of cosmological modes with modes that have a lot of noise, from the galaxy, because that's really going to screw you up at sort of this leakage. And if we just take the point of view that the simulations aren't accurate, we can just, with appropriately defined off-diagonal elements, say, oh, well, suppose we only know this to, 30% or so. How much will we get? Will our analysis get messed up by having these mixing modes? On the other hand, if there is no mixing between these modes, then you shouldn't worry that much. So in the flat sky approximation, well, noise is going to come in a bit with weighting, but we're basically interested in bias. So where you go over and over the same region, if the beam is wrong, that's going to sort of give you the wrong recovered sky map and in a consistent way. And then if you consider, as in equation 5, you have this sort of small perturbation of this transfer matrix, then you can sort of figure a covariance. So sort of the model is that the uncertainty of the beam is, zero bias, random process. If you knew it were biased, then you would just correct that. So that's a bit the philosophy. And in this sort of first analysis, we're ignoring polarization. And that's something we later want to look at, and the galaxy is polarized, and there's a lot more complicated frequency dependence with the polarization. So this is a big issue that for the moment we have ignored. So this is, well, as we all know, there's the M-mode formalism for the drift scan. But just to make things a little more tractable, we're going to make an additional assumption that we have these strips and that there's also sort of infinite density of strips. So they're very closely spaced. So you can, this sort of changes your radio survey to something that's a little more like optical astronomy with a point spread function. And then we'll see how interferometry can be sort of put into this formalism. So this idea that we're sort of scanning also in the direction north-south is sort of a fiction, so that we can do a lot of this analytically. And there are, of course, calibration problems that might be a reason why this isn't the whole story. Okay, with interferometry, with these two sort of drift scan in both directions, things really don't change that much. So here we have a visibility with, different baselines. So this is B, is the separation between the two dishes. And this sort of is in equation 10, sort of modulates your primary beam. So B of theta is just the primary beam on the sky, and it's sort of proportional to the intensity. We would, in a treatment with polarization, there would be Stokes indices. So there would be 4 components to be, here we're assuming that the sky signal is unpolarized, so we can just have a scalar beam function. And then we get this matrix M, which is basically summing over all these different beams, and we get a covariance. So this is sort of just standard matrix algebra, a little like CMB map making. And this is because of the drift scan and the fiction of a drift scan in the transverse direction. So we can do a bunch of maths, and basically your primary beam in Fourier space gets shifted by the B, and so you have these beams that are centered at different places in Fourier space. But the problem, or the error that you're looking at, is sort of an equation 19. You have some sort of a kernel, which you would like to be a delta function, but it's sort of moving stuff around in the because of the having the wrong beam, it's changing k parallel. So K perp, the wave number in the sky direction, is conserved because of this drift scan approximation. So in M modes, it would be that the different M's don't mix. And here it's with a further approximation, the ALMs don't, I mean, those sectors don't mix with each other. It's block diagonal. So we're really worried about sort of fictitious moving around of power in K parallel, which is, you know, the Fourier transform of the frequency direction. So here's some formulae for this error in the kernel. So this is the error in the map. And then, I mean, so this is completely mathematics. It doesn't tell you what you, how bad it is. So you need some sort of a model. So the idea here schematically, and I'll show you some plots that are based on sky models that Kavi made, is that we sort of divide the modes into cosmological modes that have high signal to noise, very little galactic contamination, and then dirty modes that are just all galaxy. And I mean, you sort of see that it's the off-diagonal elements that you're worried about. So if KCC is wrong, well, we're going to get the normalization of the cosmological signal wrong, but you know, that'll just be like a bias. That's not that big of a deal. Whereas it's these leakage modes that you have to worry about. So that's going to come out of the primary beam. And we haven't put these together yet. Carla does have Fourier transforms of the beam after all the apodization that she's explained to you. So here's some plots, and there's sort of three components. The cosmological signal, so this is from the extragalactic power spectrum traced by the H1 emission. Then there is the galaxy. So the galaxy doesn't vary much with, I mean, the frequency dependence is smooth, and that's sort of reflected in the fact that this becomes dark very quickly. And this is a log base 10 scale. So going, you know, even slightly green means going to, I mean, the two orders of magnitude is a small change in color. The noise, on the other hand, I think this is because the array layout that Kavi assumed, I don't know exactly what it is, but you know, there's about a factor of 3. So this is that some baselines are better represented than others. And here we have, this is a linear scale, the signal to noise. And you see that there's a sort of bright spot where you get a signal to noise per mode of about 8 or so. And what we're really worried about is the modes that in the beam that are going to take power from, can you see my cursor?
Yep.
Oh, okay. So here there's a lot of power from the galaxy, and you can see that's, you know, the signal to noise to zero. And then if you have modes in the beam that'll take that over there, then, you know, that's a big problem. And I mean, this, we haven't done it yet, but the idea is to have to look at different redshift, and we also want to sort of look at where the where we want to measure to see the baryon acoustic oscillations, but you can make a figure of merit in this way that gives you an idea of what is a good beam and what is a not so good beam, at least for doing these, for doing intensity mapping. So this is just a sort of quick and dirty figure of merit. Before you would want to design something, you would want to do more complete simulations, but if you're sort of optimizing the off-axis telescope and seeing if it can do better than Hirax for the same beam size, well, this might be a good way to start. And this is sort of independent of the rest of the system. Maybe not completely, because the noise level does come in. And I mean, if modes are too noisy because of the instrument, then they just don't get counted as being important. So you might get different results for different noise levels for your instrument. So let's see. Well, I think maybe I'll just say a little about the last point. I think we mentioned most of the other points. So in terms of electromagnetic simulations, these sort of antennas are kind of unique because they're not like in Planck. Your optical elements are many wavelengths across, so you would use physical optics. It's basically geometric optics plus. If we had a tiny sub-wavelength dipole antenna, that would also be kind of trivial. But here we have structures that are sort of in between 10 wavelengths or so. So that means that what seems good from a point of view of ray tracing optics will not necessarily be that good. It also, I mean, I think also intuitively, one way of seeing why an off-axis configuration might be a lot better, and this is sort of a bit hand-waving, but if you think of this can as just like a black spot on the pupil, then the can is pretty big, then that is just dispersing and creating its own side lobes as if you had an aperture of that size. So you get very large side lobes from having something that blocks the beam. But there are other problems. The secondary has to be very big because you can't make it smaller than a wavelength. So it doesn't look anything like the optical, Cassegrain or Gregorian telescopes, or actually the different configurations are used because with optical telescopes, you have a secondary to make a wide field of view. That's really the only reason. And here we just have a single mode. So this sort of gives you a taste of what we're thinking about and working on, and it would be interesting to hear your comments and ideas. So thanks a lot for your attention.
Thanks a lot, Martin. Does anyone have any questions for Martin?
So
go ahead, Inju.
Okay, so I have two quickly. So Martin, do you mind to reverse back to the first slides of your equation previously?
This one?
Yes. So I mean, these are all very interesting. So I think my first question is that P Gao and P extragalactic. So look like the Gao that only depends on these two, these K perpendicular K parallel absolute value, whereas the extragalactic is only related to the norm of the K vector. And what is that? And what is the assumption built into this?
Well, okay, so for the cosmology, and we're ignoring redshift distortion. I mean, this is homogeneity and isotropy that gives you this. So we're sort of putting little boxes out, and the flat sky approximation to have this formalism, but yeah, basically homogeneity and isotropy.
So that is P extragalactic, right? And P Gao, why P Gao only the absolute value?
Oh, well, well, okay, we have to do a little of cheating with the galaxy. So I mean, everybody knows the galaxy is bright near the galactic plane, and especially toward the galactic center. And if you look, outside of the disk, up and down toward the galactic poles, the galaxy is a lot less bright, but not completely zero. So this is where we're doing some degree of violence. So we would have different power spectra for, different heights above the galactic plane. But I think it is sort of a good idea to mathematically to represent the galaxy as approximated as a Gaussian random field. So the K-perp would be, I mean, if we take the Planck synchrotron maps, or say we take 30 gigahertz, well, that's supposed to be similar to the CBAS maps and, the Haslund maps and all of that. So there is a sort of smoothness and frequency. And that's sort of reflected in K parallel. So appropriately defined and rescaled, there would only be power at K parallel equal to 0. And the cosmological modes would be, if I want to measure a certain K at some redshift, if I choose a mode that is where that K factor is directed or has a large component along the direction of sight, line of sight, then that would have a very small galactic contribution. So that would be a high signal to noise mode. Whereas if that were small, if it were parallel, then it would sort of get mixed up with the galaxy. I should just say that I think looking at the literature that the exact form of the spectrum is, there's not really much data. So a lot of the stuff seems to be just guesses, but this is the whole philosophy behind intensity mapping.
Okay, and the other quick question is your delta M. I can understand your M is like antenna beam response to your underlying signal. So you convolve that to obtain a D. And then here, equation 5 is your assumption where you perturb the M. And you said the delta M is assumed to be a Gaussian random number, which with mean 0 and some variance, which is probably equation 6. I wonder, is this assumption true? The perturbation of the antenna beam is a Gaussian random number with mean, because I feel antenna configuration is quite complicated and it has a lot of parameters, and so it depends on which parameter is really being perturbed. So that's something I want to ask. Yeah.
Well, what else would you do? I mean, we want to model that it's not completely known. So we want there to be some uncertainty.
Yeah. I mean, I guess this is all perturbative approach, but I wouldn't take perturbative approach unless I simulate the whole thing and demonstrate it's small.
Yeah, I mean,
no, I don't deny this approach. I'm just saying perhaps it's better to test how big is this delta M and what is really statistically this delta M behave. Yeah.
How would you measure it? I mean, this is sort of one of the questions. We could compare different packages, different simulation parameters. We could try to measure it with drones and all of that. I think you're raising some really good points. So that this is something that we and other people should think about. Well, how do you assess these antenna uncertainties?
Mm.
And this work hasn't been done.
Okay.
Boom, you had a question? Is the same what you wrote on the chat?
Yeah, I just have some comments, not really a questions. You mentioned that far side lobe is worrisome, and I agree, because with Hirax paper, we found very strong foreground leakage that contaminate power spectrum when a bright point source appear in the far side lobe, even though the far side lobe may have very low response. If a bright source show up, it can have strong leakage. So I think that's is one of the test case that should really be done if you want to see if these figure of merit can be applied in real observations. Just my comments and thought on that.
Yeah, I think we wanted to think about the ground and reflections off of other antennas and things like that separately. So that this was, this sort of flat sky approach was sort of something that we would concentrate on first.
Yeah, that's fair.
Yeah, but it's a good comment. Thank you.
Yeah, absolutely.
It's definitely something that's going to be a problem.
Okay, is there any other question for Martin or Carla?
Let me just say one thing about the, some people assume that the ground and is a sort of perfect black body, and that the only thing the ground does is sort of add additional noise into your detector, sort of loads your detectors, but that is not, that's half true. And I think it's pretty close to half true. So this is a big problem, but just having said that doesn't really tell you what to do in terms of analyzing this problem.
I'm just thinking, Martin, if the ground matter less with fiberglass dish design, because the fiberglass should block some signal reflecting back from the ground, right? It's not like in the edges case where you really just have an antenna sitting on the ground. In that case, yes, the ground and the soil layer all matter. But for these Hirax design with fiberglass, it's just, I'm not sure. Carla might actually know better on these, or the values for sure.
But it's, I mean, there's a metallic sheet on it, so it would be diffraction, right? That would have stuff go to the ground. I mean, it doesn't matter if you have a metal mesh or metal on fiberglass, or that's my understanding.
Yeah, for sure.
But Martin, you said this is half true. What is the other half?
That it gets reflected back up into the sky or wherever.
So if the ground was a perfect conductor, everything would just reflect up, but because it's absorbing some of the energy, you still have energy loss there. But how much will depend on a lot of factors, like what type of ground it is, the moisture content, etc. So it's very hard to model.
So we were going to do, we haven't done this, but one idea was to do a simulation where you just put at the level of the ground a perfect conductor sheet. That's very easy to do in these simulations. And then thanks to the French military, a perfect black body, this is possible to, you know, be put in your simulation. I guess a lot of this antenna stuff is for sort of military applications. So there's sort of, what was it? In 1984, they developed this, you change Maxwell's equations in your layer so that you get pretty much zero reflection at every frequency and every angle of incidence. So if you subtract those two and look at the far field pattern in the sky, for example, you'll see how much your main beam and side lobes in the sky change from the reflections off the ground. So that's something simple you could do, but it's just an order of magnitude estimate of what the ground could do.